general relativistic Boltzmann equation and applications. So this talk will be about matter in general relativity, specifically about kinetic theory, so a kinetic gas. And what I want to do in these 3 hours I have available is to try to derive a fluid theory, so relativistic fluid theory, including dissipative corrections from this Boltzmann equation, okay? So yeah, so why is this interesting? So first of all, so I think one fascinating thing is that you derive macroscopic phenomena from macroscopic theory from a microscopic laws of physics. Okay, and then of course, if you do this in the general relativistic setting, then somehow this brings together general relativity and statistical mechanics. So right, so that's interesting. And then, of course, you want to give a description of relativistic fluid dynamics, as I said, including dissipative effects, so that would be viscosity and heat transport. And historically, say, so starting from kinetic theory, which is like a well-formulated and understood physical theory, this has then motivated various theory at the phenomenological level, like irreversible thermodynamics, extended thermodynamics, divergence type fluids, and so on. Okay, but also other fields where kinetic theory is heavily used is, for example, in galactic dynamics. So in galactic dynamics, the gas, now the constituents of the gas, instead of being molecules, are now the stars themselves. So a galaxy is like, I don't know, something like 10 to the 10 stars. So you can also, it is usually being modeled also using kinetic theory, collisionless in this case. And then other applications, of course, are plasma physics at high temperature. So temperature is very high, so that you have to use relativistic corrections, such like quark-gluon plasmas, fusion reactors, and so on. And then also, there's also the case where gravity comes in if you have plasma physics, not only at high temperature, but also in strong gravitational fields. Like if you have an accretion disk around a black hole, like, for example, which are crucial for this observation for Sagittarius A star, the black hole in the center of our galaxy. Okay, and then, as I said, so what I want to do in this course is to derive a fluid theory from kinetic theory. So in the non-relativistic setting, it is well known that that kinetic theory provides a method to derive the Navier-Stokes equations from including the expression for the thermal conductivity and viscosity from the Boltzmann equation. So actually, this is related to Hilbert's 6th problem. And then we're going to ask, so in this course, what is the correct relativistic generalization of the Navier-Stokes equation? So the Navier-Stokes equation, they have, of course, a parabolic component, so you have infinite speed of propagation. In a relativistic theory, this cannot occur. So, of course, we should have a hyperbolic instead of parabolic equations. So that will be one of the main goals, say, to one of the main properties this fluid theory should satisfy. So in this course, I'm going to describe a little bit how to formulate relativistic kinetic theory. So I'm going to tell you at least how the Boltzmann equation is written down, what the terms mean, and so on. But first of all, from a philosophical point of view, if you like, so like general relativity, the theory should obey the principle of general covariance, because now we formulate it in a general relativistic setting. So of course, the nice, the most elegant things to do this is to formulate the theory using the differential geometry language, because then automatically things will be defined in a coordinate-independent way. Now, for many matter models in general relativity, so that includes a scalar field, electromagnetic field, a perfect fluid, and so on, you can get away with just differential geometry and the space-time manifold. So you have a 4-dimensional manifold, M, the metric G, and then from this you construct Levi-Civita connection, covariant derivative, and so on. Okay, but for relativistic kinetic theory, because we are doing kinetic theory, the appropriate description is actually on phase space. Okay, so we have to this is, and the phase space, as we're going to see, is a suitable submanifold of the tangent of a cotangent bundle associated with the space-time manifold. Okay, so and you can choose either the tangent or cotangent, so both are completely equivalent due to the presence of the metric. So in this course, we'll choose a cotangent formulation because it's more naturally adapted to the Hamiltonian framework statistical physics is usually based on. Okay, so the main goals of this course. So there are 3 goals. So the first goal, I have to point here, so that's unusual. Usually I point here. So the I'm sorry. So the first goal would be to provide, sorry. Okay, so the first goal would be to provide a manifestly covariant formulation of the relativistic Boltzmann equation. So this is something that is well known, but I would like to take some time to explain to you, since it's a course, how this Boltzmann equation arises. So this Boltzmann equation describes the time evolution of the distribution function, which describes the state of the dilute gas. Okay, and we are going to do this in an arbitrary space-time manifold with some certain properties, which I'm going to formulate soon. So that it will be the content of lecture 1, which we're going to do today. Then in lecture 2, that will be tomorrow, we'll see that the Boltzmann equation has like preferred solutions, say a particular solution which describe global and local thermodynamic equilibrium. So they are characterized by having 0 entropy production. So I'm going to describe those in lecture 2. And then we are going to do a formal perturbation scheme to describe near equilibrium configurations. And then in the last lecture, which will be on the first day, we'll derive then the first order fluid theory obtained from this perturbation scheme and discuss its viability as a physically sound theory. So by physically sound, what I mean here, so the goal would be to derive a theory which incorporates these 4 properties. So first, it should be described by well-posed equations, also by a well-posed Cauchy problem, so that at least locally in time you can predict what's happening from giving data on a Cauchy slice, say. It should have, as I said before, causal propagations, or no superluminal speed of propagations. The global equilibrium configuration should be stable. And then also the theory, the fluid theory should have an entropy flux with non-negative entropy production. Okay, so this is what I'm going to try to show to you. Now, before we start, some brief historical remarks. So this relativistic kinetic theory was started by Hüttner in 1911. So what Hüttner did, he generalized Maxwell-Boltzmann distribution function to the relativistic case, and then he derived the, if you want, the equilibrium thermodynamic properties of such a gas. So this was in the context of special relativity, of course. Singe in 1934, he had the idea of a kinetic description taking the world line of particles instead of position momenta. And of course, this was important for the covariant description of the theory. Werner Israel in 1963, he then gave the generalistic description of the Boltzmann equation and gave the first derivation of the first order fluid theory based on the Chapman-Enskog approximation, which I'm going to discuss tomorrow for a simple gas. Okay, and this has led then to the development of transient relativistic thermodynamics, like more phenomenological level, and so on. Now, more recently, so it was thought for a long time, actually, that, I mean, in these theories, that you had to go to second order to get stable equations. And I mean, so it was thought that these first order equations that were obtained were not stable, and not even, so it was not even clear if they were well posed. And then if you went to second order, then usually one could fix things. But more recently, there has been quite some work in what is now known as BDNK theories. So this is due to this authors, Benfica, Disconsin, Noronha on one hand, and Koftun on the other hand. And they actually show that you can write down at the phenomenological level a first order theory, which is well posed, causal, and has stable equilibria. Okay, and so what I'm going to do in this lecture is actually derive such a BDNK type theory, starting from kinetic theory. And I'm going to do it in the most simple settings. So we are generalizing now. It's what you can generalize to arbitrary dimensions or to mixture of gases, electromagnetic field, and so on. But for simplicity, we are going to restrict ourselves to a simple gas. So that means a gas which consists of identical massive particles, which are spinless and electrically neutral. And I'm not going to take into account quantum effects. So, okay, and then we are going to stay in 4 space-time dimensions. Yes. Yeah. Yeah. Right. Yeah. So it's first order in the deviation from equilibrium. And I'm going to define this tomorrow more precisely what this means. So there will be an expansion parameter, which is called the Knudsen number. And this will be the first order in this parameter. And stable means that the equilibrium configuration should be stable. So more precisely, what's usually it's that a global equilibrium should be stable in Minkowski spacetime. So I'm also going to say more about this in the third lecture. Yes. Yes. So this might sound, yeah, well, obviously it should be stable, but actually that was a huge problem during many years, that many of these theories, they had unstable equilibria. Yes. So this is local in time. So yeah, yes. So typically one linearizes the equation, yeah, and then yes, that's right. Yeah. Okay, yeah, and these are the, I mean, this is also in the abstract I send. So these are the 3 essential papers. This course is based on. Of course, this means not that these are the only relevant references. There are many relevant references, but they will be cited in there, just for the notation and so on. So let's kick off with lecture 1. Okay, so in lecture 1, so today, so the goal would be to explain to you. So I cannot derive everything in 1 hour, but at least I want to tell you how this general relativistic Boltzmann equation, what it is, okay? And basically it will have 2 terms. So one is a transport term and the other is a collision term. So I will try to explain each of them so that at least you know how it is defined. So today there will be a little bit of differential geometry. So as I explained, this is because of the phase space, the relativistic phase space. So we are going to talk about this. The cotangent bundle, we'll see that there is a nice geometric structure, a natural symplectic structure. You don't even need a metric for this. Then we're going to talk about the free particle Hamiltonian, which in this Hamiltonian formulation generates the Liouville vector field. So the kinetic gas, you can imagine that between collisions, this particle, they move freely. So that means in the general relativistic setting, they move on future time-like geodesics. And then I'm going to explain the collision term and then what you actually get from the distribution function. So the space-time observables, such as like the stress energy tensor and so on, then you can couple this to the Einstein equations if you like. So something about the notation. So as mg is going to be a 4-dimensional C infinity smooth, connected, and time time-oriented Lorentzian manifold, I use this signature convention minus plus plus plus. So Txm is just standard notation, and Tx star m denote the tangent or the cotangent space at event x. Okay. And then sometimes I'm going to use this f. So if we have a smooth manifold n, fn, xn, and lambda pn, denote the class of smooth functions, vector fields, and p-forms. Also, I'm not going to use. I'm going to use a little bit today p-forms, but not extensively. Then there's a x0 derivative. So if I have a p from omega, I can hit it with the d, this d operator. This converts a p form to a p plus 1 form, and d squared is 0. And then also we have the interior derivative with respect to a vector field. So this maps a p form to a p minus 1 form, and also ix squared is 0. So Greek indices, they're going to refer to 0, 1, 2, 3. Latin indices is going to be 1, 2, 3, so just as spatial components. And eventually, we will also see tetrad indices, so that refers to an orthogonal frame of vector fields. Okay, and I'm not going to be worried about units, so we just set the speed of light and the gravitation constant to 1. So the first definition, this is the cotangent bundle. So this is the pair of xp's, where x is a point on the manifold, and p is a covector at x. So it is a fiber bundle. So you can think of it like if I point x here, then this is and I fix x and vary p, then this would be the fiber. There's a natural projection map, so which maps xp to the base point x. And then the fiber at x, that's the inverse image under the projection map of the base point x. So that will be diffeomorphic to the cotangent space. Okay, and then if you haven't done this exercise yet, then I invite you to do this first exercise. So to show that this is an 8-dimensional smooth manifold, and on the top of it is orientable, even if M is not, it is orientable. So the hint, if you want, is to, if I take a local coordinate chart of M and put coordinates x mu on them, and now on this tube here over this coordinate chart, if I take a point xp, then to x, I mean, enunciate the corresponding coordinates x mu, and then the point p I can expand in the basis of one form, the x mu, and the components p mu. This will give me the other 4 components. Okay, so you have 8 coordinates that you construct in this way, and now the exercise, the first exercise, is show that this is if you take an atlas on M, then in this way you obtain an atlas of the cotangent bundle, and all the transition maps are actually volume and orientation preserving. So this is the picture that you have. So you take 2 intersecting charts, so they will give rise to like these 2 cylinders, and then one part of the cylinder you can identify with this other part of the cylinder. And if you look at the Jacobian of this transition function, then you will see it has this structure here. So where M is invertible, and you see you have here M, and here you have M inverse. So if you compute the determinant of it, you will get 1 actually. So that's why you have an oriented atlas. Okay, now, so now, of course, you can look at the vector field on the cotangent bundle. And of course, in these adapted coordinates, now you can expand this vector field in this basis, in the vector basis d by dx mu, d by dp mu. The next thing you can do, you take this projection map and the differential of it. So this will map at a point xp. It will map a vector at xp in the cotangent bundle to a vector, a tangent vector on M. Okay, and if you write this in terms of these coordinates, then you can easily see what it does. It just erases this vertical part here. So you just, if you plug this in, then it will just erase this part here, and you get x mu, d by dx mu. Okay, and from this now you can define a natural one form on the cotangent bundle, which is called the Poincaré or canonical one form. And it is given like this. So theta, we call it capital theta. So it's a one form. So you have to feed it with a vector at xp, say. Okay, and what you do, you take this vector, this tangent vector on the cotangent bundle, you project it. So now you have a vector here. You have a vector on the manifold, and now you can pair it with p because p is a covector, right? Okay, so that's a linear. It's linear in x, of course, so that defines a one form. And if you take the differential of this one form, then you get a two form, which is called a symplectic form. And then the next exercise is to show that in these coordinates, these adapted local coordinates, theta, you can write as p mu dx mu, and lambda x, you can write as dp mu wedge dx mu. Okay, so these are like, if you know a little bit about Hamiltonian mechanics, then these are like well-known expressions. Right, and now why is this called a symplectic form? Because it satisfies these two important properties, right? So the first one is that omega s is closed, okay, and it's also non-degenerate. And that makes the cotangent bundle a symplectic manifold. Okay, in the proof, so the first property is immediate because omega s is actually exact, so it is closed also. And then to check that it's non-degenerate, you can just, for example, take this two form, you plug in an arbitrary vector field in the second entry, say, and then you get out this expression here. Now you see that this is zero if and only if both components, I mean, all the 8 components are zero. Okay, so that is what it means. So it's not non-degenerate. Okay, and now you can define this to for your Hamiltonian formalism. So that means given a smooth function on the cotangent bundle, okay, you can now show that there exists a unique vector field, which we call the associated Hamiltonian vector field, which is called XH, such that this identity here is satisfied. So that means DH is a one form, but of course, because omega s is non-degenerate, you can, it is dual to a vector field, okay? And this vector field XH is unique, and this is called the Hamilton vector field, okay? And you can also write in terms of the inner derivative, if you like this. And again, explicitly in terms of adapted local coordinates, then you find this expression here. Okay, so this is a direct consequence of if you compare this with the differential of h, then you get immediately this expression out of it. And now what are the properties of this vector field? If I look at the integral curves associated to this vector field, then you see they satisfy, and I parameterize again these integral curves in terms of these adapted local coordinates, x mu and p mu, and they satisfy these equations. Okay, and these are exactly the Hamilton's equations of motion. So you see what you have achieved now. We have provided like a geometric way of writing these equations, these Hamilton equations of motion. Okay, so through this symplectic form, and note that so far we haven't used the metric at all. Okay, so this is all independent of the metric. Okay, now the metric comes in. So because now we know we don't want any, we don't want just any trajectories, but we want to somehow describe free particle trajectories. And the Hamiltonian for this is what is called a free particle Hamiltonian. And it is this function here in the cotangent space. So you take 1/2, the 1/2 is just convention, and then you take the inverse metric and evaluate twice at p, or in coordinates, you can write it like this. Okay, and the associated Hamilton vector field is called the Liouville vector field, which plays an important role in the following, and it has this expression. Okay, so this comes from dH by dp mu. If you derive this with respect to p, then you get this, and then the second one is when you differentiate this with respect to x, so then you see you get this expression here. Okay, and now the next exercise is to show that if you now take this particular Hamiltonian and you compute the integral curves, you project the integral curves on the space-time manifold, then these curves will be geodesics. Okay, so what you need to do is just you take the Hamilton's equation of motion, so that's one way of solving this exercise, and then you eliminate p mu using the second equation, and you get a second order equation for x mu. And this second order equation for x mu, that would you can check that this is exactly the geodesic equation on the space-time. Okay, where gamma, mu, alpha, beta are the Christoffel symbols here. Okay, so in some sense, if you want, this is now a form of lifting these geodesics to the cotangent bundle and look at them as an integral curves corresponding to L. Now, another nice feature is, of course, geodesics can cross, as we know, on the space-time manifold. But when they cross, they have different tangent vectors there, because otherwise it would be the same geodesics. But if you look at it in the cotangent space, then of course these lifts, they don't cross because they belong to different p's, so they go through different points of the fiber. Okay, and now going back to the question, what is the relativistic phase space? So the physical momentum, of course, is not an arbitrary covector, but it is restricted to be, as I said before, future directed time-like, because they should describe the particles of the trajectories. Furthermore, if we look at a simple gas, as we are doing in this course, then the particles will have a fixed mass m. So that means that p mu and p mu should satisfy these conditions. So the square of p should be minus m squared. And that leads to the following definition. So if m is larger or equal to 0, then we can define at each point x on the manifold the future mass hyperboloidal. So that's just the covectors p's, which are normalized, adequately normalized, and the corresponding vector is future directed. So that's a subset of the, a submanifold of the cotangent space. And if you vary x also, you get what is called a future mass shell. So that's a pair of points x and p, where x is in m and p is in this future mass hyperboloid. Okay, and then what you can show, if m is larger than 0, then this future mass shell is a 7-dimensional submanifold of the cotangent bundle. Okay, and furthermore, the nice property is, as this Liouville vector field we have just defined is tangent on this submanifold at each point of this manifold. Okay, so you can restrict, you can look at the Liouville vector field also as a Liouville vector field on this submanifold. And the proof is very simple. If you just have to notice that this future mass shell is a level set of the Hamiltonian. Okay, because remember the Hamiltonian was essentially the square of p. Okay, so if you look at the differential of h, then because of this property of being of L being a Hamiltonian vector field, I say to h, then you have this identity here. But now this is never equal to 0 because the Liouville vector field, you see, if you look at this component here, for example, this is never 0 if you're on the mass shell because p cannot be 0. Okay, so that means, that this is different from 0, and hence dH is different from 0, so it's a regular submanifold. And furthermore, if you plug in dH of L, then because this is omega is antisymmetric, then this is 0. So that means H leaves L leaves H invariant, so it is tangent to this. Now, for those of you like topology and differential geometry and so on, here is an exercise. So now suppose MG is connected, but we don't necessarily assume that it is time-oriented. And now define not the future mass shell, but the mass shell in general. So this is just a pair of points XP where I just put in this normalization condition here. And this is, I assume also that M is positive here. Then you can prove that MG is time-oriented if and only if this gamma M is disconnected. And in this case, it consists of two components, so which will be the future mass shell and the past mass shell. Okay. Okay, now there's some things I'm going to leave out to make progress. So you can there are some more structures you can introduce on the cotangent bundle. There's a natural metric, which is called the Sasaki metric, which you can use to, you can induce it on this 7-dimensional mass shell. And that turns this mass shell into a Lorentz manifold, a 7-dimensional Lorentz manifold. And then you can show interesting things. For example, you can show that the Liouville vector field on this mass shell is geodetic and generates an incompressible flow. And this is very useful if you want to understand the physical interpretation of the one-particle distribution function. But I'm going to skip that for this course because it's not going to be essential for what I say next. Okay, so now we are going to formulate the relativistic Boltzmann equation. So the relativistic Boltzmann equation is an integral differential equation for the one-particle distribution function. So the one-particle distribution function is a function on the future mass shell. And it should be also, for the physical interpretation, it should be non-negative. And the Boltzmann equation then has this form here. So the left part is just a Liouville vector field that acts on F. Okay, and then there's a quadratic term, which is called the collision term on the other side. So here I copied again the Liouville vector field from above. Okay, and I don't have time to explain exactly where this comes from, but intuitively, if you want, F is basically telling you which trajectories are occupied or not by particles. So then, of course, if there are no collisions, so if Q is 0, then of course the number, if a trajectory is occupied once, it will be always occupied. Okay, so that just means that F is constant along the integral curves of L, along the geodesics, the lift of the geodesics, if you want. Okay, but then due to collisions, sometimes particles collide, and we're going to describe this now in the remaining part of today. Then, of course, this will modify a little bit F. Okay, so for example, like in this picture, you could have two trajectories, say P1 and P2. They are occupied, but then a collision occurs here. So the collision, it redistributes the momentum, the momenta. So these two particles, they will collide here at X, and then they will produce two other particles, P1 star and P2 star, and they may now be so this will change the occupation number basically of these trajectories, and that's what this collision term describes physically. Okay, but at least I want to describe it to you mathematically, how it is defined. So to do that, let us then look at binary elastic collisions. So we're going to assume that the gas only interacts through binary elastic collisions taking place at some event X. Okay, so I have two incoming momenta, P1 and P2, and here a collision takes place, and then I have two outgoing or post-collision momenta, as they're called, those are pre and post-collision momenta. Okay, and now you see this defines to you another manifold, which is called the collision manifold, CX. Okay, and this is these four tuples P's, so P1, P2, P1 star, and P2 stars. Each of them is in the future mass shell, such that this condition is satisfied. So this condition comes from the requirement that you want for momentum conservation. So assume that the interaction at X preserves energy and momentum, and that's why this equation come in. And then you also ask that P1 is different from P2, just because otherwise it's not really a binary collision. Okay. So despite of this appearance, it's not a linear manifold because each of these P's are restricted to the future mass hyperboloid, which is not a linear manifold. And what you can show actually is that, as I defined it here, this collision manifold is actually an 8-dimensional manifold. And it has this topology R to the 4 cross S2 cross S2. And we're going to discuss the idea of the proof. So because we're going to need it to write down this collision term. So to do this, you describe the collision as follows. So you parameterize it in a very nice way. And this is the following. You introduce the relative speeds before and after the collision. So this is Q and Q star. So Q is P2 minus P1, maybe this vector, and Q star is like the difference between the P's after the collision. And then you define center of mass moments, which you can also define. So this is basically P1 plus P2, but there's a normalization here. Before and after the collision also. And the next exercise, what you can show is actually the magnitude of this relative speeds. They're actually the same. So the magnitude of Q is the same as the magnitude of Q star. And then once you know this, you can show, and then that's directly from this energy, from this form momentum conservation. Then because you know Q, the norm of Q is the same as the norm of Q star. So you see that the center of mass momentum before and after the collision are the same. Okay, and this normalization condition you put in so that this is again normalized. This again lives on the future mass shell. Okay, so PCM and PCM star the same, and they satisfy the mass normalization condition. And then the last point you check that Q and Q star actually are orthogonal to PCM and PCM star. Okay, and that means also that they are space-like vectors. And in view of this, and then you can show also, I mean, I should have said this before, but conversely, you can also show that given a vector in the future mass hyperboloidal and two tangent vectors or covectors which are orthogonal to PCM and have the same magnitude, you can reconstruct like a binary collision using this formula. Okay, but, oh, sorry. So basically what it means, you can now parameterize your collision manifold using the center of mass moment, the magnitude of Q, and then these two normalized, I mean, Q hat and Q hat star, okay, which are orthogonal to PCM. Okay, and so this gives you R3, this gives you R, and this, I mean, this is a spatial vector. I mean, it's orthogonal to PCM and it's normalized, so this gives you the two S2 factors here. Okay, and actually it's interesting because if you don't, oh, I'm sorry, I'm going the wrong direction. If you don't require that P1 is different from P2, then actually it's not a differential manifold. You actually get like a conical singularity or something like this. Okay, and now you can, so there are two, oh, I'm sorry. Here, okay. So let me go back again. Okay, here. So there are two Lorentz invariant scalars that you can construct on this collision manifold. So one is the norm of the relative speeds before or after the collision, is the same. Okay, and then you can introduce also what is called a scattering angle. So that's the angle between Q and Q star. which we're going to assume it is between 0 and pi. And now to formulate the collision term. So the collision term will depend on what is called the differential cross section. So that's something that comes in from microphysics, so that like your friends from particle physics would tell you, depending on the nature of the interaction, they will be able to compute this for you. And it depends on these two Lorentz scalars. And this is assumed now to be a positive function, unlike the gas is collisionless. If it's collisionless, and this would be exactly 0, but otherwise this is a positive function by nature. And now you can write down the collision term. So this is this integral here. So this is the right-hand side of the Boltzmann equation. So you have an integral over P2. So say you want to compute this at point x P1, then you have to integrate over the mass shell with the variable P2. You have to integrate over this Q hat star. Okay, so this is the relative deviation between P2 and P1 after the collisions. Then you have here what is called the invariant flux. So the invariant flux is just this this expression, which depends on the magnitude of the relative speed. Okay, so in the Newtonian case, this will go away. I mean, you assume g is much less small than 1, and then you just have 1. You just have m squared g in the Newtonian limit. But in the relativistic case, you have this, bless you. Then you have the differential cross section, and now here comes the quadratic part. So you have here the product of distribution functions evaluated at the post-collision piece and the one at the pre-collision piece, okay? And this volume element on the mass hyperboloidal, in a orthogonal frame, you can write it as this way. So this is the Lorentz, which is called also the Lorentz invariant form, and px plus n. Okay, so that's the mathematical definition, if you want, or the formal definition at least for this collision term. And now, of course, you have to solve this very difficult integral differential equations. Some exercises. So, of course, here, sorry, in the what I just told you. So here, of course, you give P1 and P2 is an integration variable, and Q hat star. So how do you construct P1 star and P2 star from this? You can show it easily. You can do this by means of this formula. So if you know P1 and P2 and G, and I mean G you can construct because this is the relative speed. And then if you have Q hat star, then you can construct in this way. And then there are also some important symmetries, and one has to take into account. So the collision manifold has this discrete symmetry. So of course, if you interchange P1 and P2, then of course nothing happens. The same if you interchange the post-collision momenta. But then you can also interchange the pre and post-collision momenta, and it will be it will stay the same. Okay, and now the next exercise is actually to show that the differential cross section is invariant with respect to all these symmetries. Well, if and only if it satisfies this property. So if you replace theta by pi minus theta, then it should give you the same answer. So these exercises are simple. Here's a more difficult exercise, so which we are going to use heavily tomorrow. Suppose you have a function on the future mass hyperboloidal, which is a collision invariance. So collision invariance means that f of P1 plus f of P2 is equal to f of P1 star plus f of P2 star for all possible binary elastic collisions. So for all P1, P2, P1 star, P2 star in the collision manifold, okay? Now the statement is that this is true, so this f satisfies these properties if and only if it has the following form. So if f is a constant plus a linear form in P. So this is going to be very important for, let's say, tomorrow, okay? So the if part, of course, is direct. Of course, if f is a constant, then of course this is satisfied. Also, if it is linear in P, then this is also satisfied, but the challenge here is to show that this is I mean, the only if part here is more difficult to show. All right, so to summarize what we have done so far, so I told you how the relativistic Boltzmann equation is written down. So it's an integral differential equation for the distribution function, which is a function on the future mass shell. And here it is summarized. So the left part is called the transport or the streaming term. And this is governed here by this Liouville vector field. And the right-hand side is this integral operator, which for binary elastic collisions has this particular form. And yeah, we have used these abbreviations here. All right, so in the last part of the lecture now, if you solved the Boltzmann equation, what do you do with the distribution function? So what physics do you get out of it? So, and to describe this, we're going to do the following thing. So we are going to pass to the, if you want the weak form of the Boltzmann equation with respect to the momenta. So in other words, we're going to take a smooth test function on the mass shell, okay, and integrate over P, both sides of the Boltzmann equation, okay? So on the left side, you will have this integral here. And on the right side, you will find this expression here. And here, we have used heavily the symmetries that I mentioned before of the collision manifold. So you see if I just, if I just multiply by psi here and integrate over P1, then I will have just psi 1. But now you can interchange P1 and P2. So instead of having psi of P1, I can write psi of P1 plus psi of P2. And also I can interchange the post and pre-collision momenta. And then you get this identity here. Okay, so one star, one star, and so on, that refers, it's evaluated at P1 star, for example, okay? Okay, and this would be the volume form on the collision manifold. Now, the nice thing you notice about this formula is that the right-hand side is automatically, I mean, is always 0 if psi is a collision invariant. Of course, also if psi is constant, for example, then this is 0. But also if psi more generally, I mean, if it's linear in P mu, then this bracket will vanish. Okay, so that's the first observation. And now the second observation is you introduce now these S moments of the distribution function. So that means you define a symmetric tensor field like this. So you integrate over the future mass shell, the distribution function. And here you put S times P, evaluate at the vector fields Y1 and YS. And then you integrate this over the volume, over the mass hyperboloid, the future mass hyperboloid, okay? So this defines a symmetric tensor. Again, in adapted local coordinates, it has this form, so T mu1, mu2, mu_s would just be the integral of F, and then you have S momentums here, and then you integrate over the mass shell, okay? You can do this for any S. So these are the S moments of the distribution function. And you have the following proposition. So if you compute so this is actually an identity, so it has nothing to do with the Boltzmann equation. So if you take any smooth enough F, say, and you compute the divergence of T, okay, then this will give you the Liouville vector field that acts on F, and then you have one less P that appears here, okay, because you contracted here, say, mu1, so here you have only mu2 and mu_s, okay. And this identity, you can prove it in you can prove it very geometrically also, but the easiest proof, say, is that you fix X, and then you introduce Gaussian normal coordinates at X mu. Okay, so at this particular point, the metric is just diagonal -1 + 1 + 1, so the Minkowski form. And furthermore, at this point, the first derivatives of G are 0. And now you compute the divergence on the left hand. I mean, you apply the divergence here, okay, because the Christoffel symbols are 0 at x, then this is just an ordinary derivative. So you can pass it under the integral. Here you have to be careful with the volume form, but again, because of this property, you can write it in this way. And then basically you just get a directional derivative here. So these p's, they don't depend on x. X and p are independent coordinates. And then, but then if you use Gaussian normal coordinates at x, then this is equal to the Liouville vector field. Okay, so this p mu d mu 1 will give you the Liouville vector field at x on f. And now we have established this at the point x in these particular coordinates. Because of general covariance, this now holds in arbitrary coordinates and for arbitrary points. Okay, now let us go. So having, oh, sorry. So having said that, now we go back to this identity, to this integral identity. And now let's evaluate, let's see what happens if I use this test function equal 1, then this goes away. So the right-hand side is 0. But now I apply my proposition to the left-hand side, and I can rewrite this as a divergence. So if I apply this integral identity to psi equal 1, then I get the divergence of j 0, and j will be the first moment of the distribution function. So this integral here, and physically what j mu represents is a particle current density. And this is the continuity equation. If you do the thing for the remaining collision invariance, so you take psi as one of the components of p, say, then you obtain this equation. You obtain that the divergence of t mu nu is 0, where t mu nu is the second moment of the distribution function. Okay, and that is the energy momentum stress tensor, or the stress energy tensor. Now, what you can, I mean, I don't have time to explain why this should be the particle current density and is the energy momentum stress tensor. You can go to the Newtonian limit and then convince yourself that this is correct. But here's an exercise. What you can show is that if the distribution function at x is positive, and it is smooth, say, then you can show that j mu is automatically future directed time-like, okay, as the current density should satisfy. And t mu nu of x satisfy all the standard energy conditions. So it satisfies the strong, dominant, weak, null energy condition, and so on. So the weak energy condition, for example, is that you contract t mu nu with two time-like vector fields. And then you see you will get something quadratic here if you do that. And if f is positive, then this will automatically be positive. Okay. Okay, and so summarizing, any solution of the Boltzmann equation satisfies these two, what I'm going to call balance laws. Okay, so you have the divergence of j mu is 0, and the divergence of t mu nu is equal 0, where j mu and t mu are given by these expressions. Of course, you could compute the divergence of higher moments. But then this will not be 0 anymore. So then, because then the collision term will give you that something that is different from 0, but that's usually the starting point for the moment, for the method of moments in the kinetic theory. So that's interesting, but I will skip that. And then now what is important here, the fact that this t mu nu that we have constructed is symmetric and satisfies the balance law. This balance law here, if the Boltzmann equation is satisfied, of course, that allows you now to couple this gas to the metric. So if you want now to consider the gas to be self-gravitating, what you would do, you would solve, I mean, you would postulate this Boltzmann equation on the top of the Einstein equations. So G mu nu here is an Einstein tensor, kappa is a coupling constant, and you put here the stress energy tensor, okay? And then this is, of course, automatically consistent because of the contracted Bianchi identity. So if I take the divergence of G mu nu, this is, of course, identically 0, but you don't get an additional equation from this because this equation, as I showed you, implies that this is divergence free. Okay, so you can couple this to the gravity in a cell-consistent way. And actually, there's been early work by Bansel and Choquet-Brouillard in the year I was born, where it is shown that this yields a well-posed Cauchy problem. Even I think in this work, they included also, they looked at the charge gas, they include also the electromagnetic field. And there's also other more recent results I don't have time to summarize, but which is more the cosmological setting where like future stability of some cosmological space-times for a Boltzmann gas. And of course, in a collisionless case, there has been many more work, many other works. But I'm not going to go into that. So in the next two lectures, what we are going to do, we are not going to solve Einstein's equation. So we are going to assume that the space-time is given to us. It could be a black hole space-time. It could be a Friedmann-Robertson-Walker space-time or anything else. It is given to us. And then we're going to try to solve the Boltzmann powers, okay? And of course, it's very hard. So especially if the collisions are present, as we do here. So we are going to look at particular solutions first, where this collision term is exactly 0, and then I will discuss like a formal perturbative expansion and show you how, when you truncate this perturbative expansion to first order, you get a fluid theory. And the fluid theory basically will be based on these balance laws that you have here in the theory automatically. But then when should, of course, it's not a complete theory because you have 14 unknowns here for 5 equations. So you need equations like an equation of state and equations that connects somehow, that relates these 14 unknowns. Okay, and then this will be done then in the next lecture. Okay, thank you. Yes. No, as far as I know, they proved local, well-posedness, local in time. However, more recently, there has been some work where I think they if I'm not mistaken, they prove like the maximal. Oh, okay. You're asking about maximal. Sorry. Yes. Yeah. Okay. I don't know. I should check. Yeah, I should check. Yes. Sorry. Yes. So what I want to say that there have been some recent results also in cosmological, and there I think they have global well-posedness in the future direction. Of course, cosmological because it's expanding and expanding, then it's a little bit easier than Minkowski, but still it's a impressive result, I think.